Hi everyone, this is my thesis defense presentation. My name is Meghana Govind. I study at Round Rock High School and I'm from Austin, Texas. So this research revolves around neuro and immunology through the study of autoimmune diseases. My hypothesis is lipid nanoparticle mimicry of ACH to increase immune tolerance and in myasthenia gravis. So before we dive deeper, I just wanted to share why I conducted this research. So I have family members who experienced their fair share of autoimmune diseases, and I saw their struggles, and this exposure made me pursue research related to autoimmune diseases. So here's a quick overview of my presentation. So let's dive right into the introduction. So what is myasthenia gravis? Myasthenia gravis is a chronic neurological autoimmune disease that targets nerve to muscle communication. Currently, MG affects 700,000 people worldwide, and although MG is considered a rare autoimmune disease affecting less than 1% of the population, I believe that making an impact or a difference in those lives of even that 1% can be truly impactful. So common symptoms of MG can range from minor coordination difficulties and vision impairments to severe breathing abnormalities. And normally, the brain will send a signal to the muscles to carry out a specific action. So, for example, if I want to move my phone from here all the way to the other side, a signal from my brain is sent. But in MG, the signal is disrupted. So this causes patients to have difficulties with doing simple tasks. And these symptoms can limit the patient's ability to carry day-to-day life activities, which can impact their lives greatly. So what causes MG? So the immune system mistakenly attacks the acetylcholine receptors as it can't differentiate between the body, which is itself, and external stimuli. And so this causes a production in autoantibodies and abnormal B cells, which produce those autoantibodies and can lead to symptoms. So in the figure, we can see that the autoantibodies are intercepting the signal between the acetylcholine and its receptors. Additionally, as of right now, we don't know the causes of MG and effective cures. So what do I mean by effective treatments? So currently, the most commonly used treatment for autoimmune diseases are immune supplements, which are powerful drugs that try to suppress abnormal immune cells. However, there is a huge downside to this, which is that it's not targeted, so it affects normally functioning immune cells as well. And this can cause patients to have side effects and can worsen their well-being. So my goal is to go down to the root of the problem, and by using lipid nanoparticles to mimic the acetylcholine receptors to trick the immune system and to increase immune tolerance overall. Okay, so methodology. I was able to create a strong base for how lipid nanoparticles can mimic AChR to increase immune tolerance in myasthenia gravis by a systematic literature review. I based my research on well-credited research papers from PubMed, NIH, Cleveland Clinic, and many more to create a well-grounded hypothesis and research paper. Here are some of the asks of the different websites. Okay, now moving on to the discussion, why lipid nanoparticles? So lipid nanoparticles have exceptional biocompatibility. So this is because of a specific part of lipid nanoparticles that are called ionizable lipids, which have the capability to change their reactive or reactivity and charge due to the specific pH levels it's interacted with or it's exposed to. So for example, lipid nanoparticles can be positively charged, but when it's interacted with the bloodstream with a pH level of 7.4 approximately, then it turns neutral, which decreases reactivity and can be used to our advantage. Additionally, size is very important when it comes to choosing the correct nanoparticle. If a nanoparticle is below 20 nanometers, then it can be flushed out through the kidneys. And if it's above 200 nanometers, then it can be detected by immune cells and promote immune response. So lipid nanoparticles, however, fall right between this range and typically range from 50 to 150 nanometers, which works for us. They also have the ability to be functioned with PEGs, antibodies, and specific ligands, which make them powerful tools in membrane replication. So there's also specific types of lipid nanoparticles, and I'm using the pegylated biomimicry lipid nanoparticles. These are also known as stealth lipid nanoparticles because they can replicate natural lipid proteins in our bodies and can reduce immune activation. So this allows for the insertion of the main immunogenic region, MIR peptides, onto the lipid nanoparticle surface, which can more accurately mimic receptor compounds and have high binding affinities for autoantibodies. We will get to this discussion in further slides. Okay, so the main immunogenic region, MIR, and residues are common biomarkers for AChR. So these main factors help autoantibodies recognize the receptors. This is really important because lipid nanoparticles have to replicate this accurately in order for them to trick autoantibodies into binding to them instead of the actual receptors. So how do we coat lipid nanoparticles into having the main immunogenic region and residues? So synthetic peptides, amino acid chains replicating the 69 to 67 amino acid sequence, which is a 10 compound sequence, is kind of like the heart of the main immunogenic region, part of the extracellular domain in AChR. So if lipid nanoparticles can be coated with this, then their mimicry efficiency can increase. Additionally, engineering other crucial residues like asparagine 68 and aspartic 71 to lipid nanoparticle surfaces can also increase their mimicry efficiency. This also increases immune tolerance overall, and this contributes to it because it breaks the vicious loop between autoantibody production and the receptors production as well. So what I'm saying is that as autoantibodies continue to degrade these receptors, the body starts producing more receptors to, maintain homeostasis. However, B cells recognize this, the abnormal ones, and they start producing even more autoantibodies, which is just a continuous cycle of production. So with the play of lipid nanoparticles, autoantibodies can actually start to bind to them instead, which leads to the overall decrease in receptor production, right? So B cells will then recognize this and kind of train themselves into realizing that AChR are friends and not foes, leading to trained immune cells. Okay, conclusions. So what are my major findings? So lipid nanoparticle mimicry of AChR is an innovative way to counter autoimmune diseases by sparing AChR and restoring their functions by drastically reducing symptoms for patients. This allows them to have happier and healthier recovery process while still receiving the care they need without the reliance of immunosupplements. This targets the root problem of MG. And yeah. Just stop sharing. Okay, I just wanted to thank Dr. Christina and Professor Burgle for carrying me through this whole process. Writing a 4,000 word research paper was not easy. So them being so passionate about this whole research program really inspired me and motivated me to keep going, push through. And yeah, I'm really thankful for the whole Gifted Gabber team for helping me out and giving this amazing opportunity. Thank you.
Excellent. A question from Dr. Lilova.
Thank you. Your topic is also a very difficult one. It's very interesting, though. I was thinking about something while listening to your presentation. So, autoimmune diseases are generally very complex, very difficult to treat. So do you think that your solution could be applied to other autoimmune diseases as well?
Yeah, absolutely. So, the cause is still the same. These abnormal B cells are still producing autoantibodies, but they're just programmed to to target different areas. So, for example, MS, multiple sclerosis, is another neurological autoimmune disease that affects the nervous system. So, if we program or engineer lipid nanoparticles to coat with the myelin sheath, which those autoantibodies are affecting, then yeah, we can potentially use this application into other autoimmune research.
Thank you. Great.
Yeah.
Great work.
Wonderful. A question from Professor Virgil.
Okay, good. Congratulations, Meg. Job well done. All right. So, based on the findings of your research, um, do you think that it could be further improved or replicated in the future?
Yes. So I really feel like there's a few gaps in my research. So taking it further, going through lab experimentations can really further analyze this whole research topic and can potentially grow into other fields as well. So I feel like just with more time and more experiments in future developments, I feel like it can have a lot of more potential.
Thank you.
Wonderful. Wonderful. Thank you, Meghna. Wonderful job.